Hi everyone. In this video I'll be talking about the area and perimeter notes and also 12.1 and 12.2. My original idea was to have you guys kind of measure circles and rectangles in our classroom. So in lieu of that, what I'm going to do is kind of keep it simple with the area and perimeter. Let me go to an example. Actually, I'm just gonna skip most of this stuff and just talk about a couple examples. So imagine we had a rectangle and we wanted to find the area. The area of a figure is basically the two-dimensional space within some boundary. So for a rectangle, any rectangle, if you have the length and the width of that rectangle, then the area will be length times width. For perimeter is a bit different. Perimeter is where we're counting up the length of the exterior. So the perimeter of a rectangle, we would have L, W, but we also have L and W over here. So if we add up everything, we would have 2L plus 2W. Right, we have those like terms, L and W, we add them up. So if I wanted to find the area and perimeter of this particular one, so for the area, we would have the length of 10 times the width of 5, and I would have 50. And if this were inches, let's say, inches, then I would have 50 square inches. So what that would mean is that there would be 50 of these square inches that would fill up this space. For the perimeter, if I wanted to know the perimeter of this thing, so we would have 2 times L, so 2 times 10 plus 2 times 5, right, using this formula here. So in that case, I would have 20 plus 10, in other words, 30, and that would just be linear inches. Right, I'd have 10 over here, that's 20. 5 plus 5 is 10 more, so 30. What about circles? So circles have a totally different formula. So for some general circle, if you have a radius, so we call the distance from the center of the circle to the exterior of the circle the radius. And if you have radius r, then the area of that circle would actually be pi, this special number pi, times r squared. So this is that special number 3.1415 dot dot dot. The perimeter, sometimes called the circumference of the circle, would be actually 2 times pi times r. So let's imagine I wanted to find the perimeter. I'll just do that one first. I would have, well, if this is r for this particular circle, let's imagine this is 3 inches. Then I would have the perimeter as 2 times pi times 3. So I could just leave it as 6 pi inches. For the area, if I wanted to know the area of this particular circle, then I would have pi times the radius squared. So I'd have 9 pi square inches in that case. All right, so just a couple of quick examples about how to find the area and the perimeter of a rectangle and a circle. Let's go on to 12.1. This is going to be kind of the meat of our discussion today. So we've seen a few different models. Just to summarize, we have seen relationships between quantities that grow what we call linearly. For an example of this, if you let y represent the amount of money you owe the movie theater and let x represent the number of tickets you purchase, then the relationship between the amount you owe y and the amount of tickets you bought x would be a linear model, right? For every new ticket you purchase, you get this similar jump in money. So for each new ticket, you have the same jump in the price of $12, right? So for 0 tickets, $0. For 1 ticket, $12. For 2 tickets, $24. For 3 tickets, $36, and so on. So this is a linear relationship. It's not as though, like, when you buy the 4th ticket, that's free or something, or a reduced price or a greater price. That wouldn't be nonlinear in that case. Here's a nonlinear example. This is one that grows rationally. So if you let y represent now the temperature of a pan and let x represent the time the pan has been on the burner, then we have the square root of x plus 70, perhaps as a model. So here I've grabbed the pan from the cupboard and I placed it on the burner. So it just has some room temperature, beginning temperature, and then it begins to heat up as the burner begins to work. And then the temperature, if you kind of map the temperature over time, it'll approach this setting that I've set on the stove. And this line is not a straight line. Although it looks fairly straight down here, it's actually curved all the way throughout. Okay, so that would be a nonlinear relationship. You're getting a different temperature for the same chunk of time. Right here, you're getting the same price for the same chunk of tickets. Here, we're getting a different temperature for the same chunk of time horizontally. We have seen recently these quadratic models. So if you have y represent the height of a ball, and you let x represent the horizontal location of that ball, then you would have maybe this as your quadratic model to match the trip of this ball. So now we're going on to exponential models. And this is going to hit, hopefully not too close to home, but I wrote these problems before this pandemic, but now this type of example is maybe a little too real at this point. Let's read it though. It says, for example, imagine you have contracted a virus. At this moment, there is one viral cell in your body. Suppose that the cell is able to replicate itself in 1 hour. Let's form a table of values that track the population of the virus with respect to time. Okay, so what we're going to want to do ultimately is try to figure out like what the model is. But let's just form a table first. So let's start with 0. So 0 hours after you contract the virus. In other words, right as that one cell enters your body, we would have one viral cell. And then the supposition is that it can replicate itself in 1 hour. So just to draw a picture of that, here's this one cell. After 1 hour, it has now turned into 2 cells. Okay, so after 1 hour, we would now have 2. Let's imagine another hour passes. So these new cells have inherited that ability from the ancestor cell. So it's not as though all these are still present. Literally, this 1 turned into 2. Now that 1 is not in existence anymore. Now this 2, after the second hour, have turned into 4. So now there are these 4 after 2 hours. Okay, if I just draw another line, each of these cells now replicates itself in another hour. Okay, so I'd have 8, right? Now 8. So after the third hour, I would have 8. Okay. After a fourth, I'm not going to draw a picture, but I would have now 16. You can start to see this. Okay, ultimately what we want to do is say, okay, what about just after H hours? Right? We don't want to stick with this in particular because we want a model. So something to note is that 16 would be the same as 2 to the fourth. 8 would be the same as 2 cubed. 4 would be the same as 2 squared. 2 would be the same as 2 to the first. And 1 would technically be the same as 2 to the 0. So what I want to point out is that this number, it looks like, has just become the power over here. And this number has simply become the power over here. This number has simply become the power, right? I'm repeating myself here, but this is the pattern. So if I want to say just after some H hours, the model would be 2 raised to the H, right? There's no indication that I should deviate from this pattern. So the model, maybe I'll call it the population as a function of H, something like that, would be 2 to the H. All right, and I developed this table to be able to see that. So how many viral cells are present after 1 day? So H is in hours. So I would be finding P of 24 for 1 day. So 2 to the 24th. Let's see how many that would be. So this is a lot of viruses. We have 16,777,216 just in this 1 day. We started with 1, and 24 hours later, there's almost 17 million. So I'll say this would equal 16,777,216. I've also learned since writing this problem that it's not really correct to say cells. I'm not a biologist, and my biologist friend pointed that out. They're not really cells. They're not really living things. They're just these kind of protein capsules. So kind of weird, but they're not biological. If medical attention is required for the virus once it reaches 2 billion cells, when should you go to the doctor? So in a little bit, we'll have a more precise way of figuring this out. But what I'm going to do is just use my calculator to estimate this. So 2 to the 24, we already know is the 16 million. This question is saying, how many hours do you need to wait until there are 2 billion cells? So what if it's 30 hours? Ooh, okay. So for 30 hours, we'd have, I'm trying to read what number this is. This would be 1 billion, right? There'd be a comma there, there. So that would be 73 million. So that would be 1 billion. So let's see, if I go to 31 hours, I'm now up to 2 billion. So I'm going to try to hone in on where this occurs a little more precisely. So maybe 30.9. So if you see this, 30.9 we're now at this 2 billion figure. So I'll say when H is about equal to 30.9 hours. So about 30.9 hours after contracting the virus, medical attention is needed because we're reaching this 2 billion mark. Okay. Let's go on to page 124. So here's kind of a general model right here. Something to note is in the one we just had, we had P of H equals 2 to the H. So technically I had like a 1 out here, even though I didn't write it. So I would technically have A of 1 and B is 2 for this particular model. Something to note is that A is like the starting amount, right? That A, our starting amount was 1 viral cell. So if we started out with 100, I would have 100 out here. Okay, let's see another example. So it says the number of ants at a picnic is growing rapidly. At 11 a.m., 5 ants find the picnic. Each hour after 11 a.m., 3 times as many ants have found the picnic. At A of H, or let A of H represent the number of ants at the picnic H hours after 11 a.m. It says write an equation for a model of A of H. Okay, so at this preliminary stage, what I'm going to do is use another table. Okay, so over here, I'll have, this will be H, and then I'll have, this will be A of H over here. So let's look at what's happening 0 hours after 11 a.m. And then we'll look, since it says each hour, I'll just skip by 1, 2, 3, and then I'll go to 4. So over here, it says at 11 a.m. So that's my 0 hours after 11 a.m. 5 ants find the picnic. So at 0 hours after 11 a.m., the population, which I'll write over here, is 5. An hour passes. 3 times as many ants have found the picnic. So that means in 1 hour, I would have 15, right? Every hour that passes, there are 3 times the previous amount. So after 2 hours, 3 times 15, I would have 45. 3 times 45, then another hour has passed, so now 3 times as many ants find the picnic. 45 times 3 is 135. 3 times, another hour has passed. So I need to take 3 times this amount. So 405. Something though about this is the pattern I think is a little bit hidden. So what I'm recommending is to not actually carry out these multiplications. I'm just going to have 5 here, and then I'll just write it as 5 times 3. Here, I'll write it as 5 times 3 times 3. This would be 5 times 3 times 3 times 3. This would be 5 times 3 times 3 times 3 times 3. Right, just to show you what I mean by that. 5 times 3 times 3 times 3 times 3 is 405. Writing it this way, though, makes the pattern appear. So this would be the same as 5 times 3 to the 4th. This would be the same as 5 times 3 cubed. 5 times 3 squared. 5 times 3 to the 1st. And then technically, this would be the same as 5 times 3 to the 0. And then that pattern reveals itself, right? When it's written this way, it's hard to see the pattern, but when you keep it expanded, then the pattern is a little bit more visible. So the model, A of h, it looks like if I generalize this to some h amount of time, that I would just have 5 times 3 raised to whatever that amount of time is. So that's 5 times 3 raised to the h. That's not 53, that's 5 times 3 raised to the h. Okay. Estimate numerically when 11,000 ants will be at the picnic. So with A of h equals 5 times 3 raised to the h. Oops. So what I'm going to do is kind of experiment with my calculator. So 5 times 3 raised to the whatever. What I'm trying to do is figure out what h produces about 11,000 ants. So for 5, I get 1,215. So I need more time. For 6, 3,000, 7, 10,000, right? This is very, very close. So maybe it's like 7.05. Good. So maybe I'll just bring that back down a little bit. This is estimating. We're going to have a much more precise way of doing this eventually. So I'll say h equals about 7.01 hours after 11 a.m. Okay, so that's just using the model and the calculator to estimate it, right? That's all we were trying to do, was estimate. That's the key word. Part 3, how many ants will be at the picnic at 11 p.m.? So 11 p.m. means h equals 12. Because for us, everything happens at 11 a.m. This is h equals 0 right here. So 11 p.m. would be 12 hours later. So I'm finding h of 12. So I'd have 5 times 3 raised to the 12th. So I get this amount of ants. So 2,657,205 ants. All right. Just to summarize, remember up here I was saying that A is like your starting amount. B is kind of like how things are evolving. So notice here's our starting amount, right? It said at 11 a.m., 5 ants. There's that 5. And then each hour after that, 3 times as many. So here's that 3 times. So that's no coincidence, right? That 5 is the starting amount. That 3 is the base of the exponential. So if I said there were 10 ants and 4 find the picnic every hour, I would have a 10 and a 4. I just wanted to go through the table to kind of show the pattern. But if you're seeing things, you can just write this down. Let's try another one. Here's a slightly different case. So suppose the virus you had contracted is now being treated with antiviral medication. When the medication was administered, there were 2.2 billion cells. If medication kills a third of the cells every 4 hours, find a function that models the population of the virus as a function of time. Okay, there's a lot more going on, I think, here. I'm going to start with another table. So over here, this will be my time. So I'll call this hours again. Here I'll do some calculation, and then maybe over here I'll write the model that is suggested by that. So 0 hours. Let's do this different color. So 0 hours. Well, it said that at the time that the medication was administered, that there were 2.2 billion cells. So what I'm tracking here is the population. Okay, so I'll just write it as 2.2. So this will be in regard to billions. So that'll be the true population. So this is my calculation, not much calculation needed here. Just have 2.2. So now what I'm going to do is not go to hour 1, because it said every 4 hours. So I'm now going to go to hour 4, because that's when this interesting thing occurs, right? It's not every hour that this third takes place. It's every 4 hours that this third takes place. So what I'm doing is tracking the living population. So if a third die off, that would mean that 2/3 survive, right? So I'd have 2.2 billion times 2/3. This would be the new living amount. So I'd have 2.2 times 2/3. Another 4 hours. So skip to hour 8, right? This is now our true amount, right? This is the current amount. So I take that current amount, and then only 2/3 of those survive. So I'd have 2.2 times 2/3 squared. Go to another 4 hours up to hour 12. Here is our previous starting amount, but only 2/3 of those survive because a third die off. So I'd have 2/3 times 2/3 times 2/3. So that would simplify to 2.2 times 2/3 cubed. Ultimately, what we want to do is say, okay, what about just some h number of hours? Okay. So for h number of hours, well, it looks like, just to try to identify a pattern, when I had a 12 here, I have a 3 there. When I had an 8 here, I have a 2 there. When I had a 4 here, technically I didn't write it, but there is a 1 there. Right? When I had a 0 here, oops, I didn't write it, but technically you could write a 2/3 to the 0 here. So if I have h hours, it looks like I'll have 2.2 times 2/3, and it's not just simply h, right? Because it's not 12 and 12. It looks like 12 got divided by 4. Looks like 8 got divided by 4. Looks like 4 got divided by 4. It looks like 0 got divided by 4. So I would have h over 4. So the model, I'll just write it here. Maybe I'll call it P of h, would be 2.2, and that's in billions, times 2/3 raised to the h over 4. That's the model to track the living population. Part 2 says, estimate how long until there are less than 100,000 cells remaining in your body. Okay, so what we want to try to figure out is, if we want to know 100,000, we want to know when this equals or is about equal to, I'll just go ahead and write it out. its full glory, this 2.2 billion. This is 2.2 million, so I need 3 more zeros. And then times 2/3 raised to the h over 4. So I was just writing 2.2 up here to save room, right? It's really this beginning amount, not just 2.2 cells. So what I'll now do is use my calculator. Make sure that I type this in. So here's comma, comma. So this looks like 2.2 billion, and then times 2/3 raised to the something divided by 4, and I just need to kind of mess with this something. So let's see after 10 hours. Nope, nowhere near 100,000. What about 50 hours? Nope, nowhere near 100,000. What about 100 hours? Okay, we're under 100,000, but maybe I can kind of zoom in a little bit more. That's pretty close. That's farther away, I guess. What about 98? So here we have maybe 0.5 more to go. Maybe 0.59. Nope, still not under. Maybe I'll go to 0.6. Still not under. Let's go to 0.7. There we go. So I'll estimate it as 98.7 hours. So H equals about 98.7 hours. So just to clarify, what I'm doing is I'm just typing in the model that we have and messing with H to see what value for H gets this result to dip below 100,000, right? And when I had 98.7, I still have divided by 4, because that's our model. It dips just below 100,000, okay, for this number of hours. Okay, moving on. Just some straight up solve cases, and then definitely check out the key to see the solutions to the rest of them. But basically on these, you're just using your calculator to try to solve these. So if I'm looking for 5 to some number equals 125, 5 squared equals 25, 5 cubed equals 125. So x equals 3. Right? Down here, we're looking for what x makes this true, if any. So 3 times 4 raised to something might equal 192. If it's equal to 5, that's way too large. If it's equal to 4, still too large. It's equal to 3. There we go. X equals 3. X doesn't always equal 3. Let's see here. So for example 7, again, we're just looking for the base now. So something raised to the 5th, and we want that to equal 7,776. Maybe it's 3 again? No. 4? Nope. Let's see, 5? Nope. 6? 6. Okay. So x equals 6. Another way of doing that that's less kind of guess and check. To get rid of this power of 5, what you can do is raise both sides to the 1/5 power. Powers to powers multiply. So when these multiply, I'll be left with 7,776 to the 1/5 equals x to the 5 times 1/5. This would equal x to the 1st, In other words, 7,776 to the 1/5 would equal x, right? When you have a power of 1, oops, when you have a power of 1, you have solved. So if I were to type that in, raised to the 1/5, then I would get my 6, and that would tell me, oh, that x needs to be 6. So I guess I already wrote that down here. All right, I'll talk to you all next time.